Welcome back to the Math Professors. I'm going to do another proof by induction. My previous proof by induction was the sum of the first n integers. So if I have 1 plus 2 plus 3 all the way up to n, that the formula for this is going to be n times n plus 1 divided by 2, and I'll link that in the end of the video. What I want to do now is the sum of the first n squared. So what I'm really asking for is this is going to be equal to 1 plus 2 plus 3 plus plus n, but instead of like the previous one, what we're going to do is we're going to square all of these. And my claim is that the sum of the squares of these integers is this formula right here. And let's just see it work for a couple cases. So when n equals 1, that's just going to be the very first one. So it's just going to be 1 squared. Well, if I plug this in here, 1 plus 1, 2 times 1 plus 1 all over 6, you can see that this is going to simplify to 6 over 6, which is equal to 1. And like I said, 1 squared is equal to 1, so we got that. Now let's try it for the first two. Well, that's going to be, the addition of those two, which I have here. So the sum from k equals 1 to 2 of k squared should again be this formula with n equals 2. So 2 plus 1, 2 times 2 plus 1 all over 6, and we can see that this is going to be 2 times 3 times 5 over 6, and those will cancel, so this is equal to 5, and we can verify it. 1 squared plus 2 squared is indeed 5. And then finally the last one, just to double check, the first three, 1 squared plus 2 squared plus 3 squared, using the exact same formula, we can see that, this adds to 14, and it gives us 14 using the formula. Now, with mathematical induction, this is what we're going to have to do. You start out with verifying the first case. So I've already done this. This is step 1 here for mathematical induction. Step 2, I have to assume the nth case. So let me erase this, and I'll write that step down. All right, so step 2, we have to assume the nth case. Prove the first case, n equals 1, assume the nth case. So what that means is that the summation from k equals 1 to n of k squared indeed is equal to n times n plus 1 times 2n plus 1 all over 6. So now what I have to do is I have to verify it works for the next one. I have step 3, which is the most important one, or the most difficult one, I should say, is to verify that it works for the n plus 1 case. So verify the n plus 1th case. Now, what that would mean is this needs to be equal to, 1 squared plus 2 squared plus 3 squared plus, all the way up to not just n squared, but we have n plus 1 squared has to follow this formula. Now, what that formula is going to be is, well, instead of, stopping at n, we're stopping at n plus 1. So what I'm going to do is I'm going to plug in an n plus 1 into each one of those pieces. So this is going to be, n plus 1. This is going to be n plus 1 plus 1, so I'm going to have n plus 2. This is going to be equal to, well, we're going to have 2 times n plus 1 plus 1, right? So this is going to be 2n plus 2 plus 1, so this is going to become 2n plus 3. And then this is going to be all over 6. I have to essentially verify that this indeed is equal to this. And once that is shown, then we know that it's true. Now, here's the trick. I already know the formula for this. The first n is equal to this. So this is going to be equal to n times n plus 1 times 2n plus 1 all over 6 is going to be equal to, plus n plus 1 squared has to be equal to this thing. And that's all I have to verify. So I'm going to get common denominators. I'm gonna simplify this expression, and I'm going to show that this expression is equal to this expression. We'll start here, and then I'll finish here, and then verify that these two things indeed are the same. So starting here, what we have is this. I'm going to distribute this. This is going to be equal to n squared plus n times 2n plus 1 all over 6. Plus this is going to be equal to n squared plus 2n plus 1. Now, in order to get common denominators, I'm going to multiply top and bottom by 6, and I'm also going to expand this thing. So this is going to be equal to 2n cubed outside is going to be equal to n squared, inside is 2n squared, last is n, plus top and bottom is going to be 6n squared plus 12n plus 6, because I'm getting this common denominator by multiplying top and bottom of this by 6. And then finally, combining like terms, I'm going to have a 2n cubed. N squared, 2n plus 6 is going to be plus 9n squared. This n plus 12n is going to be equal to 13n. And then finally plus 6 all over 6. And then I have to show this side as well. So let's go ahead and expand this. N squared plus 3n plus 2 multiplied by 2n plus 3 all over 6. So this is going to be equal to 2n cubed. Outside is plus 3n squared. Now this times both, plus 6n squared plus 9n plus 4n plus 6 all over 6. And what we can see is this going to give us, I'll just kind of drop it down so they're even. This is going to be equal to 2n cubed. 9n and 6n is going to be plus, well, 6n plus 3n is 9n squared. 9n plus 4n is 13n plus 6 all over 6. And what I just verified is that this indeed works for this formula, which is just this formula for the n plus 1. So the n plus 1 case has been verified, which shows us that this equation right here is true. So if you like the content, please subscribe.